So, we're starting out with some material that I think you guys are probably familiar with. Hopefully you are. If not, if you're like, I thought this was a literature class, this is your cue. So, we are going to get into some actual material, and we can stop talking about things besides analysis and design, because I don't like talking about other things. These are more fun. So let's do this. Voltage, current, resistance, and all that. Two quantities will be of special importance in analyzing and designing electronic systems. I know, you're surprised. They're voltage and current. All right. The relationship between them defines a third important quantity, resistance, or more generally, impedance. We're not going to talk about impedance until next week, but resistance is sort of the first approximation of that. Momentarily, we will define each of these, but we start with the fundamental quantity in electronics, which is electric charge. Sometimes we just call it charge. It's a property of matter that describes the attractive or repulsive force acting on the matter in an electric field. Your notes say magnetic field there. That was just my own bias. I do a lot of work with magnetic fields. So when I wrote that, I meant to say electric, and I just typed in magnetic. So you should correct that in your notes. At the microscopic level, charge is quantized into charges of subatomic particles, such as protons and electrons, which have opposite charges, E and minus E, where E is the elementary charge. In the PDF, that's a hyperlink to elementary charge, and it's like some really tiny number of coulombs. I didn't put it in there because I didn't feel like it. Didn't want to muddy the water. You don't need to know that for any calculation that I plan to give you. Okay, charge has the derived SI unit coulomb with symbol C. It is considered to be a conserved quantity, okay, which so like a fundamentally conserved quantity in nature, so you can't create or destroy a new charge, you just move it around. So, all right, that brings us to voltage. Voltage is the difference in electrical potential energy of a unit of charge moved between two locations in an electric field. So, pretty intuitive understanding. It's a little bit analogous to if you moved a mass around in a gravitational potential field. It's a little bit analogous to that, since we're all mechanical engineers here. And electric fields are a little suspicious. We don't trust them. Gravity makes a lot more sense to us, at least to me. I don't know. So, voltage is typically given the variable V, lowercase v, and has derived SI unit volt with symbol capital V. So, a little side note, when I write my small v's, my little v's, I write them like that. I write my big V's like this, because up on the board it's really hard to tell size. So I try to do V's, little V's like this and big V's like that, just so you can tell what I'm writing. So we try to use little v for voltage and big V for, it's a unit volt. However, we do break this little convention all the time. For voltage sources, often we will use capital V, S, because sources we often like to capitalize. Because everything's just conventional. All right. Voltage is always defined by referring to two locations. Sometimes one of these locations is implicitly ground. Okay? Ground is an arbitrarily defined reference or datum voltage considered to have zero electrical potential energy. Just like in a gravitational field, remember, gravity, if you define a certain say height in the gravitational field to be zero potential energy, and everything is measured from there as far as potential energy goes, your datum. So that is what we do also with a circuit. We haven't talked about circuits yet, but in an electrical system, we define voltage as being relative to some datum, which we call ground, such that we can talk about the voltage at this or at that location by implicit reference to ground. But it's good form to describe the voltage as being between two locations or across an element, which refers to two locations. We can talk about voltage at, but we need to be careful to recognize that it means at that point relative to ground. Current, we're all ready to define current, and it is fortunately a very simple definition. It's just the flow of charge. So that's current. It's typically denoted with the lowercase I and has derived SI unit ampere with symbol capital A. And yeah, that's all familiar to us. We typically generate, so this is a little terminological thing, but it's actually a little bit more than terminological. We typically generate voltage by doing work on charges. So generate voltage by doing work on charges. Conversely, we get currents by placing voltage across matter through which current can flow. So we get currents. We think of the voltage potential difference as causing this current to flow. So causality here is quite complex, but I posit the following proposition. So we typically observe current when applying voltage. Okay? So from a phenomenological point of view, from just like observing the phenomena around us, it is natural to consider voltage causal of current. There should be an is there. It is natural to consider voltage causal of current. So if you go into, there's a whole like physics debate about causality in electronics. It's fun. I recommend, reading a couple articles on it. Nothing really becomes clear to me when I read the articles about it. But I do believe that almost everyone who works with electronics feels that voltage causes the current, because whenever we apply voltage to something, current flows. So from that standpoint, voltage causes current. On like a fundamental subatomic particle interaction, I don't know. Physicists can tell me later when they figured their shit out. So, okay, circuits. So electric circuits are dynamic electrical systems in which charge accumulates in and flows through elements. And you notice there's a couple little changes here, and I'm sorry for doing this to you, but I felt like it was clearer for me to do a couple changes. So, my bad on that. So here I say, like in your notes, it says energy storage elements. I decided to extract that concept and put it in with some others. So you'll see that in a moment. And this version is now available online, but I realize you don't have that in front of you. So circuit elements are connected via metallic conductors called wires, which ideally have the same voltage relative to, say, ground everywhere. So we just assume that along a wire, the voltage is the same, unless the wire is very, very long, in which case we have to take into account that the wire has some finite resistance associated with it. We generally assume it has zero resistance if it's short. And yeah, so that's in general what a circuit is. We combine elements. We're going to talk a little bit more about elements in just a moment. circuit topology, I did rearrange a little bit on this too. So circuit has a few basic topological features. A node is a continuous region of a circuit that has the same voltage everywhere. So a wire is often a node, right? Typically a node. In most circuits, the wire, we assume, is all at the same potential, so we have wires as nodes. Also, everything along, so like you guys are familiar with resistors that have those little terminals sticking out of them, little bits of wire. Everything along there is part of the same node as well. Okay? A circuit element, so we kind of used this term already, but we had to. A circuit element is a region of a circuit considered to be, or to have properties distinct from the surrounding circuit. Examples of elements are resistors, capacitors, inductors, and sources. So they do different things to the current and the voltage, and we call them elements. These are we talked about lumped parameter modeling last time, and these are the lumped parameter elements that we model. So a circuit element has terminals through which it connects to a circuit. So a resistor has two terminals, one on each end, and you connect that up to the circuit. Battery has two terminals, well, all the ones I've ever seen have two terminals, and all the other circuit elements you've seen for the most part have two terminals. There are other types that have more terminals than that. We'll talk a little bit about those. Circuits in parallel are those that have two terminals, each of which is shared by another element's two terminals. Okay. I'm gonna draw a circuit in a moment, and we're gonna ask questions about this. You guys all think you have a really good understanding of parallel and series. I can already tell you do, and I'm gonna try to convince you that we have to be very careful about parallel and series. So, circuit elements in parallel have two terminals, each of which is shared by another element's two terminals. Circuit elements in series are those that have two terminals, only one of which is shared between them, and this one cannot be shared with any other element. Okay, so that's this is a definition. It's just a topological definition. Now I'm going to draw a little circuit over here with just resistors. So I can't be up to anything tricky, right? Just resistors. I might draw these little circles in my circuits sometimes, or a dot. Those just mean that I'm probably going to use that as a junction, but I'm not. Don't hold me to it. I might not use it as a junction. It's just part of the same node. So here's a little circuit. No. Nothing tricky here, just a few resistors. What could go wrong? Okay, so let me ask you. I will label them R1, R2, R3, and R4. So are R2 and R4, are they in parallel, series, or neither? Series. And that's because they share a node, a terminal, I should say. They share a terminal, and the other terminal is not connected to each other. So they're in series. Now, and also there's no terminal, there's no other element connected here, which is part of the definition for series. Now, what about R3 and R4?
Well, R3 is parallel to R2 and R4.
Series.
Series of R2 and R4, wouldn't it?
So you're saying that if you were to combine R2 and R4 into a composite resistor, it would be in parallel with R3.
Yes.
That's correct. That's correct. However, it is easy to let your definition for parallel get mixed up here and think that R3 and R4 are in parallel, when in fact they're not, because they do share this node, but they do not share this node. So this one, R4 is up here and R3 is over here, and there's a circuit or a resistor in between. In addition, just because I drew this little wire out here doesn't mean that there's any current ever going to flow through it, does it? So right now I hooked it up so that, maybe you could put a voltage source here or something, but we didn't. So currently, in fact, R3 and R4 are in series right now. This is because this is just, there's nothing there. So if you delete this, no current's flowing down it because it's a dead end, right? Can't go anywhere. No current flow. So R3 and R4 share a terminal, and then on the other side, they don't share it. So that means they're in series. But if you did connect a source over here, say source, then it would split these two resistors, and they are not in series anymore because now their shared terminal is connected to a third element, and now it can't. Now it's not in series. Okay, so it's not a hard concept, but it's a tricky one. So just be cautious when you look at two elements if you think they're in series or they're in parallel. It all depends on these topological definitions here. So always go back to that. I did have a student who made it through part of this course, and who was convinced that if they were drawn on the page in parallel, that meant they were in parallel. And that was he was a really funny guy who always was being playful, and so at one point he exposed this perspective that he thought that was the case, and he got a lot of crap from his fellow students for that reason. It was pretty fun. It sort of became like an inside joke about like, oh, they're in parallel. Yeah, people even wrote it on like their final exams, like jokingly. Aren't these in parallel? Yeah. Anyways, don't think that that's the case. Go back to the topological definitions.
So question.
Yeah.
Is R1 and R3, is it parallel or series?
Oh, okay. So R1 and R3 right now, you can't say they're neither in parallel or in series at this point. If you were to combine these three resistors together, all of these, so R2, R3, and R4 into a composite resistor, then R1 and that composite resistance would be in series. Yeah. We'll talk more about combining resistance soon. Okay. Soon as in like a few minutes from now. Element types. So this is the thing that's not in your notes, and I apologize for that. For the other crew, I had them just write it alongside their topology discussion, or their circuits discussion, like over here on the side. So that's what you guys will have to do. My bad on that. The following are common types of circuit element. So energy storage elements store energy in electric or magnetic fields. So capacitors store energy in electric fields, inductors in magnetic fields. We'll talk more about those types of elements. Energy dissipative elements dissipate energy from a circuit, typically as heat, such as in a resistor. So that's what a resistor does, actually. So when it impedes that flow of current, it's also converting some of that electric energy into heat energy, thermal energy. Okay? So that's another type. Another type of element is an energy storage element, which provides external energy, I said storage, source element provides external energy to the circuit For example, a battery is a source element that provides energy to the circuit from outside. There are other types of sources as well. And finally, energy transducing elements convert electronic energy to another form. A motor is sort of the paradigmatic example, converts electric energy to mechanical energy. So those are the types of elements that you could encounter in a circuit. There are some sort of exotic types as well, but as far as energy goes, these are the only possibilities, right? You can either provide energy to the circuit, you can take it away from the circuit, you can store it in the circuit, or you can change it into another form. But energy in general, we are going to assume is conserved. We're not like doing any fusion stuff here. No fusion in this class. I know you thought there was going to be. Okay, and now we can talk about power. So electric power, there's a lot to talk about in electric power, so I don't want to just dismiss it as being a simple concept. But for now, what we'll consider in terms of electrical power is just it's the time rate of change of energy, and the instantaneous electric power, P, into a circuit element is defined as the product of the voltage across and the current through it at a given time t. So you multiply the voltage and the current at any time, and you have the power, instantaneous power, at that moment. If you're working with a DC circuit and everything's constant, then it's just whatever the voltage across the element is multiplied by the current flowing through it, and that's just constantly the power that's either being stored, or if it's a DC circuit, just being dissipated in a resistor. So we'll get more into that as we go, but essentially just remembering that it's just the product of the voltage and the current. That'll get you most of the way you need for now. So power typically goes into heat. That's actually the most common thing in the circuit for it to go into is heat, which is why Amazon in particular, but all these big tech companies have these big server farms, and one of the big problems at these server farms is heat. They got to get rid of all this heat. What are they going to do with all this heat on their server farms? And there are quite a few jobs in that right now for mechanical engineers, getting heat out as quickly and as effectively as possible. So, because the chips run better when they're not overheating. So it turns out. Mechanical work is another thing. Electric power to mechanical power. Radiated energy, so lamps, and then transmitters like a radio, for instance. Stored energy, so batteries, capacitors can store energy. Although, so you can charge up a battery. We typically think of a battery as being a source of electric energy, though, and not a place to store electric energy. Batteries are a whole thing. I don't need to go into the details right now. But the typical battery that you connect to your remote it's just converting chemical energy into electric energy, and it can't be recharged by just trying to return it. So capacitors can do that, and there are some types of batteries that can be recharged, but it's a whole thing. We don't need to do that. Terminological note, so in case you haven't read Art of Electronics at all, I recommend it. There are little gems like this in there. Don't call current amperage. That's strictly Bush League. If you've played baseball, you understand what that means. But if you haven't, apparently that's not a common term. I didn't realize that until I started using this in class. But Bush League means it's just like, kind of like, maybe there's like some people who like maybe in the sticks would use that term, but it's generally just not the best term. If you want to feel cool about yourself, always make sure you say current and not amperage. Same applies to resistance. Don't call it ohmage. That one's not used as often. But current being amperage, it's used a lot. And if you want to feel superior, use that. So you guys know that thing where if you are greeting somebody and they're like, "How are you doing?" You're like, "Oh, I'm good. You know, and I'm like, "How are you?" And they're like, "I'm well." I'm like, like, I know that you're supposed to use the other word, but I thought we were being informal here, and now you're trying to be cool. Yeah. Anyways. Yeah. That is always, I always feel, and then also if somebody says like I'm doing good, and then like if I say I'm doing well, I'm like, oh man, that wasn't cool. I'm being an asshole right now. All right. So Kirchhoff's current law. Did we skip something? Yeah. It's down here. Kirchhoff's law. So Gustav, which is a name that I think is really cool, Kirchhoff, which is a name that I really am annoyed at because I can never remember how to spell it, formulated two laws fundamental to circuit analysis. So his current law depends on the fact that charge is a conserved quantity. Therefore, the charge flowing in a node is equal to the charge flowing out of a node, which implies his current law, which is the current into a node is equal to the current going out of the node. So we often will abbreviate Kirchhoff's current law as KCL, implies that the sum of the current into a node must be 0. Assume, for instance, that K wires with currents IJ connect to form a node. Kirchhoff's current law states that if we sum up those currents, it has to equal 0. And we're familiar with that. I think we've all seen Kirchhoff's current law in physics, but it's good to remind ourselves. It can be discovered empirically, one way. The elements connected in parallel have the same voltage across them. So you could go up and measure some circuits and say, oh, well, they're in parallel. Look, the same voltage. This doesn't mean that they share the same current, of course, but it does imply Kirchhoff's voltage law, which is that the sum of the voltage drops around any closed loop is 0. A closed loop in a circuit is a series of elements that begins and ends at the same node. So if you go around for a while in a circuit and you come back to the same node, your path has been a loop. Okay? So KVL implies that the voltage drops across elements that form a loop must be 0. Assume, for instance, that K elements with voltage drops Vj form a loop. KVL states that if you sum them up, you get 0. Pretty straightforward stuff that we're all familiar with. Now Ohm, he has a lot too. Much of electronics is about the relationship between voltage and corresponding current. Through it, the functional relationship between V and I is of the utmost importance to the analysis and design of circuits. The simplest relationship is known as Ohm's law, for which we will first need the concept of resistance. So we're going to define a resistance in this class as being the ratio of voltage over current. Okay? That's what we're going to define as being the resistance. Now we're ready to define Ohm's law, which is kind of not that exciting sounding. Some materials, such as conductors, in certain environments exhibit approximately constant resistance, which is like a super weak statement. However, it's really useful. With it, we can assume for certain elements and situations that the resistance of the element is a static property and that the voltage and current are proportional. We call such elements resistors. That's what we define a resistor to be. Something for which the ratio of voltage over current is roughly constant for lots of different situations. And even the resistors that you buy that are called resistors don't behave as perfect resistors. For instance, when they heat up, their resistance changes. Sucks, because there's what a resistor does is literally generate heat. So it happens a lot that the resistance changes. So approximately, it's not that bad to consider them to be constant. So combining resistance. Resistors can be connected together in different topologies to form composite elements that exhibit equivalent resistances of their own. K resistors, so K is some number of resistors with resistances Rj connected in series, have equivalent resistance Re given by the expression just sum them up. Sum up the resistances and you get the equivalent resistance. So as long as they're in series, you can sum them up and that gives you an equivalent resistance of that series of resistors. K resistors with resistances Rj connected in parallel have equivalent resistance Re given by the expression 1 over the sum of 1 over R whatever. So in the special case of two resistors with resistances R1 and R2, what will the formula give us? So Re is equal to 1 over R1 plus 1 over R2, right? And we could rewrite that. We find a common denominator in this denominator, which is R1 times R2, right? So we end up with 1 over R2 plus R1, all of that over R1 times R2, right? Which, I'll write it over here, we can easily take the reciprocal, and, oops, not 1, you're going to want to have the ratio of R1, R2, come up to the numerator, and R1 plus R2 are in the denominator. Note that there is a pattern that emerges if you add a third resistor, but the pattern is not just bop a little R3 in there and plus an R3 in the denominator. That is not how it goes. So there is you can memorize the pattern, but that's not the pattern. So you wanted to do 3 and then you see if you can pick up on the pattern. Really common for people like, oh yeah, this formula is easier. Let's just place one more resistor in there, no problem. Try it. You'll see. Doesn't work. Okay, so now we have our example. It's a really fun example. So, understanding a circuit, answer the questions below about the circuit shown. Voltage across and current through a circuit element X are denoted Vx and Ix. So for instance, the voltage across resistor R1 will be VR1. The current across resistor R1 will be IR1. Or the current through resistor 1 will be IR1. Okay? That's how we denote our voltages and currents. The signs are defined in the diagram. So in the diagram, I've got a plus and a minus, which means that we assume the voltage drops in that direction. Well, actually, what it means is that we define a voltage drop in that direction as being positive. So if we solve for VR1, comes out positive, it means that actually the voltage over here is higher than the voltage over here. But if it comes out negative, it means, in fact, the voltage over here is higher than the voltage over there. We don't really assume anything. We just are declaring a sign convention. We'll talk more about sign convention next week. But when we assume that, our sign convention will tell us, we also assume that the current is flowing in the direction of voltage drop. Okay? All right. So what does it mean if we refer, so question 1, what does it mean if we refer to the voltage at node A? So there's node A. What does that mean? Right, yeah, it's the voltage between A and ground. That's what it means. So voltage from A to ground. Okay, that was easy. They get a little harder, not too hard. Okay. So number 2, what is the current IR2 through resistor 2 at a given time t in terms of the power it is dissipating, PR2, and the voltage across it, VR2? We're pretty early in the game here. We don't have a lot of formulas. So, and this one involves power. How many formulas do we have that involve power? Just the one, so, probably going to use it. So we know that the power dissipated in resistor 2 is, from our definition, the voltage across R2 multiplied by the current R2. And these are all functions of time, and I'm just dropping the functional dependence notation of t because it's just a lot of writing. So, we happen to know the power. It was given. Well, we want to know what the answer is in terms of power, so we don't need to worry about that parameter. That's a known parameter, even though it's not specified. And the voltage across a VR2 is also kind of given in this problem. So what I want is I in terms of P and V. And so we literally just have to solve this simple algebraic equation. So IR2 is equal to P R2. It's mostly an exercise in writing subscripts divided by V R2. And that's the current, which is what I asked for, of resistor 2 in terms of the power is dissipating and the voltage across it. Pretty much just a little manipulation of one of the formulas. Nothing to see here, really. They get a little bit more fun, though. So 3, if the source voltage, Vs, here is 5 volts, and the voltage across resistor 1 is 3 volts, what is the voltage across resistor 2? 2. And you knew that because you applied which law?
All the voltages, the sum of voltages.
Yeah, the voltage law. So KVL, Kirchhoff's voltage law, says that if you go around the loop, you can sum them up and they got to equal 0, right? So we can start anywhere in the loop and go around. Let's start here, for instance. This would be a fun place to start. So if we start there, we encounter first, we go this way around the loop. First we encounter a drop across R1, right? And so let's say that a drop we'll just put a positive sign on, and then a gain we'll put a negative sign on, just because we had to choose something. So a drop, assumed drop will be positive, so VR1. And then we have another drop, VR2, so we have to add VR2. And then we have the source, which is actually a gain, right? So it goes from negative to positive as we go around the loop in this direction. So that means it's a gain, which we've done the drops as positive, so the gain has to be negative, right? Vs. And that has to equal 0. And we can solve then for what we want to know. VR2 equals Vs minus VR1. We could plug in the numbers now, since we're at the end. 5 volts minus 3 volts equals 2 volts. Pretty easy. Just apply one of the laws. Number 4. What is the equivalent resistance of the resistors R1 and R2 combined as shown in the circuit? So our RE is what?
R1 plus R2.
R1 plus R2, and we knew that because they're in series, right?
Mm-hmm.
But we were all a little bit afraid to say it in case we were wrong. I usually don't give you things that you're gonna get wrong. I usually just ask you questions that like I think you're gonna get right. But I don't know. We're setting the tone differently this semester. Maybe I've changed. You know, people change. I believe it. So R1 plus R2, no problem. Just sum them up. And now we're down to the last one, number 5. If VR1, so the voltage drop across R1, is 3 volts, and the resistance of R1 is 100 ohms, what is the current flowing through through R2? So we don't want the current flowing through R1, we want the current flowing through R2. Now we've got some complexity. Multiple equations, maybe? It's gonna be fun. Okay, so how might we go about tackling this problem? Any ideas? We might start, so a lot of times we sort of intuit our way through these simple problems, and we're going to learn a more systematic approach later to this type of thing. But for now, one way to go is, okay, let's start with what we want to know. Do we know any equations for what we want to know? What we want to know is, what's the current through R2? Okay? We have, I have claimed, 2 equations we could write down for the current through R2. One of them is going to be Ohm's law for R2, and the other one's going to be Kirchhoff's current law. Okay? Now, Ohm's law is going to lead us to a need for finding VR2, right? We don't know VR2. Kirchhoff's current law, however, is going to lead us to identify the current through R1 and R2 as being the same. And that's the one, and current through R1 is something that we have access to because we know the voltage across R1. So that's the direction I think we should head. Now, you could just sort of try to intuit your way through it, but I would say if you try to think a step or two ahead, it'll help. So I will say KCL. So KCL tells us that if we sum up in node A all the currents going in, we have IR1, and then we have going in, and then out is IR2, right? And that has to be equal to 0. So we know that IR1, or IR2, which is what we want to know, right? IR2 is equal to IR1. And IR1 we can find because we know the voltage across it and we know the resistance. So from Ohm, we know that IR1 is equal to VR1, which we know, divided by R1, right? So, if you take these 2 equations together, it implies that IR2 equals VR1 divided by R1. And we have those numbers. They are, what did I say?
3 volts and 100 ohms.
3 volts and 100 ohms. And a little note on units. I don't typically recommend using anything besides like a base SI unit in your calculations. If you do that, then you don't have to worry so much about all the details in the calculation. In the end, when you present it, don't just use a base SI unit because nobody wants to see you write out 0.000 or 10 to the negative 10 meters. They want you to say, oh, that's 0.1 nanometer or whatever. So use the prefix on them. But this comes out to be, and this is going to come out in amps because we used 3, which was in volts, and we used 100, which was in ohms. We didn't use kilo ohms or anything like that. And this comes out to be 30 milliamps, right? 30 milliamps. That's it. Any questions? Everybody wants some lunch and then some weekend? All right, me too. Have a good one.
Thanks.